and down. When you look at a map, the latitude and longitude on a map, a trail map, for example, is always in degrees. So it's something that we're very familiar with. But quite frankly, and we use 360, so we just take a circle and we divide it up into 360 equal parts, and we use that to measure angles. But in mathematics, degrees are very cumbersome, believe it or not. And quite frankly, 360 degrees is somewhat arbitrary. There are countries in Europe that do not use 360 degrees. They use another value. I think it's 400, but I'm not sure of that. So dividing a circle into equal parts, in our case 360, is somewhat arbitrary, and mathematically speaking, it's a little bit cumbersome. So when we're doing calculations that involve sine and cosine functions and tangent, we're involving angles, we don't use degrees. We use another parameter which is called radians. And radians are based on the relationship between the diameter of a circle and the circumference of a circle. So if you have a circle here, and you were to actually measure somehow, like if you had a disc and you actually rolled it along the ground and measured how far you went, and compared that to the diameter, if you took the ratio of those two, C over D, you would get a number that's like this. They call it an irrational number. And it doesn't matter how big the circle is. It doesn't matter how small the circle is. When you take the circumference of any circle and divide it by the diameter, you always get the same ratio. And we call this pi. This, can I go over what I mean by an irrational number? Anybody want me to go over that for you? Okay. So let me show you something here. A rational number is any number that can be expressed as a fraction. So if I had this number, all the way out to infinity, the question is, can I express that number, that decimal, as a fraction? All right, so what I'm going to do is put a little bar across the 1 and the 3 to represent the fact that that just repeats itself forever. So let's see if we can do that. Let's see if we can express that as a fraction. And I'll need you to confirm this with your calculators. What I'm going to do is I'm going to let that number be x. X equals that decimal. 0.131313, etc. All right? And what I'm going to do now is multiply both sides of that equation by 100. So if x is equal to that, then 100 times x is equal to 13.131313, all the way down. Okay? Make sense? Now I'm going to subtract those two equations. So I have 99x is equal to, now here I have 13, and on the right hand side of that decimal, those things cancel out because it's 1, 3 all the way down to infinity. So on the right-hand side of that equation, I have 99x, and left-hand side 99x, right-hand side 13. So now x equals 13 over 99. Punch that into your calculators and see what you get for the decimal. 13 over 99.
On the 31.
0.131313, right? If it's another decimal at the end of the calculator, it's just a rounding error. Okay, so you cannot, intuitively you would think, okay, that's irrational, it just goes to infinity, but it isn't. That decimal happens to be a rational number. And I can show, one more example, I can show by the same technique that if I have the decimal point 99999 all the way out to infinity, I can show that that decimal is equal to 1. All right, so x equals that. And because that decimal only repeats itself, it repeats itself after one decimal place, I'm going to multiply each side by 10x. And 10x is equal to 9.999. All the way out to infinity. Subtract the 2, and I have 9x equals 9, or x equals 1. Okay? So that decimal is a rational number. So what I just showed you here, you cannot do that for this number. You cannot do it. It doesn't work. This number, 3.14159, that ratio is irrational. And that's what I mean by an irrational number. Now we don't, when we work with circles and whatnot, we don't often use diameter. So the formula for the circumference of the circle is typically based on the radius. So here we have the radius, the diameter is 2 times the radius. So that's 2 times the radius. Circumference over 2r is equal to pi, and you multiply that out and you get the circumference of a circle is 2 pi times the radius. Okay? Well, this is, even though mathematically this is something that is probably more useful when solving equations, still, in the real world, it's nice to be able to equate an angular measurement based on pi. It's nice to say, well, I equate that to degrees because I'm familiar with degrees. So if I have the radius here, and I travel completely around that circle, and the number that I end up with, which traverses that entire circle, is 2 pi, I could say that 360 degrees, in terms of degrees, is equal to 2 times my number that I came up with for that ratio. 2 times that ratio is equal to 360 degrees. This is degrees, and this is the ratio that I'm talking about over here. Well, if 360 degrees is equal to 2 pi, well then the question is, how many degrees, x, is equal to one of these numbers here? If I want to normalize that, what do I get? If all I have to do is cross multiply, and x equals 360 over 2 pi. Multiply that out on your calculators and tell me what you get. 360 divided by 2 pi.
I got 565.
57 what?
565.
567. 560.
You have to put in parentheses first.
Oh, dude.
That's on D 360.
Yeah, I did 360.
Oh, it's 57, yeah.
57 point what?
Right, 29577.
Okay, so it's 57.29. Okay, so 57.29 degrees is what we call 1 radian. So if you take 57.29, 57.29, 57.29, and you just keep it going, you're going to divide that circle into 6 parts, and then you're going to have a little sliver here left over, and that's your 6.28. 3.14 times 2 is 6.28, that's your remainder, which is equal to 2 pi. So 1 radian, one of these ratios that we're talking about here, one of them is equal to 57.3 degrees. And that's a formula that's in your text. So when you're going from degrees to radians, I think there's another formula in there that you can just write down. Make sure you do that. But that's where it comes from. So visualize that generator. That rotor goes around 1 revolution, right? Goes around 1 time. And when it does that, the output of that generator makes 1 complete cycle on our sine wave. All right? So 1 complete revolution is equal to 360 degrees, is equal to 2 pi radians. So that means 180 degrees, halfway around. 360 is equal to 2 pi radians. So that means halfway around. 180 degrees is equal to pi radians. All right? Divided by 2. And 1/4 of the way around, when that rotor is top dead center, we're at 90 degrees. And that's equal to pi over 2. And 45 degrees. Pi over 45 degrees is equal to pi over 4. And so on. And in your book, there's a chart that relates.
Does it, when it's on the under part for 90 degrees, is it still pi half or is it 3 pi?
It would be down here?
Yeah, would that be 3 pi over 2 or just?
Yeah, 3 pi over 2.
This is good to remember.
And because the sine wave is repetitive, typically in textbooks, you stop right here because the whole thing repeats itself. So you don't ever see equations where they're asking for the value of the sine wave at 10,020 pi, or you don't see that. That would be like 15, 20 cycles down the way. It's always repetitive, so everything stops at 2 pi. I mean, I have seen it in textbooks, but it's not much value. So you see the relationship between the radians and the degrees? And the position on the sine wave? It all goes back to that rotating component of your generator. Okay, I want to do one more thing, and then we're going to take a break, and then we're going to play around with your oscilloscopes and function generators. And just, I want you to get a little bit of experience playing with those. So one more thing that I want to show you. Quite often when we're working with electrical circuits, we're not dealing with just one sine wave. We might be dealing with 2, 3, 4 sine waves. You might have a power source at one end of the circuit and a power source at the other end of the circuit, and you're looking at some component somewhere in the middle, and you might have 2 sine waves that are related to one another. So you'll have one sine wave here, shown in black, and you'll have another one, let's just say, like this. It might have a different magnitude, but the key thing is that it's offset. They don't superimpose one on top of the other. And so what we want to do is be able to express the value of one of those sine waves with respect to the other one. We're going to call this one the reference. They may be the same magnitude, they may be a little bit different. And this x-axis there is going to be expressed in degrees. So here's how you do it. What you do is you take the angle between these two waveforms. You just pick a point where, let's say, they both cross the x-axis. You could pick a point where they're both at the peak. It's the same thing. It's the same angle. But we're going to pick this. We're going to call that angle phi. So this is theta, and the difference between these two waveforms is this angle right here. And let's just say this is voltage. So we have V1, which is, well, I'm going to call that V reference. And this now is going to be V2. Okay? So V2 is going to be some magnitude, whatever that is, A, times the sine of theta minus phi. So wherever I am on this wave, if I take that angle and subtract it, that's going to tell me where I am on this wave. Now you might say, okay, looks to me, what we're saying is that this red sine wave is lagging the reference. But to look at it, you say, hey, wait a second, that looks like it's leading. It looks like that's all out in front. So how could it be lagging? Well, the idea is it's a little bit counterintuitive, and here's how I keep things straight in my own head. If I grab hold of that red sine wave, which way do I have to push it so that it coincides with the black sine wave? I have to push it in the negative direction. I have to force that sine wave this direction. And so even though it looks like it's leading, it's not, it's lagging. And what you do is you take whatever that point is on the black sine wave, you subtract the difference. And that'll give you the corresponding value on the red sine wave. the fact of the matter is that by the time this guy gets going, the red sine wave, this guy has already reached a maximum and has maybe, well, it's almost reached a maximum. So by the time this guy gets going, this guy has, the black sine wave, the reference one, has already reached almost a maximum value. And at that point, V2 is starting out. So V2 is actually lagging. To look at it, it's a little bit confusing, and that's why just remember, if you're given the reference sine wave, to come up with the formula, just say, which way do I have to push the red sine wave so that it coincides with my reference? So if I have another sine wave here, like so, this is now V3. And I have another angle here that I'm going to call alpha. So V3 is equal to B, I'm going to say that's B, the magnitude, sine of theta plus alpha. So I take the reference and I add the difference, and the angular difference between the two, and I put that inside the parentheses, and that is the equation for the green sine wave. Which way do I have to push that guy to get to the reference? I have to push it forward this way. So this one is said to be leading. My reference. And again, so this, you start out here, this sine wave has hit the peak and it's started to go downhill, and at that point the reference sine wave starts to take off. So the green guy is leading the reference. The red wave is lagging the reference. Another way to look at it is you say, okay, it looks like it's leading, and just say, okay, that's wrong, it's lagging. It looks like it's lagging, okay, that's wrong, it's leading. That's another way to reference it. Just assume you're wrong. And then if you do that, you'll be right. Okay, who has questions? That's probably more than you'll ever want to know on alternating current and voltage sine waves.
Let's do the practice.
Pardon me?
Let's do the practice.
I don't really have any practices. I'm going to come up with some homework problems for you, but okay, just remember some takeaways. Make sure you know the difference between period and the frequency. Make sure you have that. Write down your equations for leading and lagging, and maybe draw a little diagram and make sure you can correlate those guys. You know the formula for RMS, root mean square. Make sure you got that down. Okay? Let's take about a 15-minute break, and then we'll play around with the oscilloscopes. A lot.